In this highlight video, we will discuss the stereoselectivity of elimination reactions. After you've watched the video, you will be able to define stereoselectivity and be able to predict products for elimination reactions where more than one stereoisomeric product is possible. What is stereoselectivity? Let's look at two examples. In the top example, we see that we have a secondary alkyl halide and we have a weak base. So what mechanism by would the elimination reaction proceed through? So weak base, this should be an E1 mechanism. So we're going to lose a proton from the beta position. Notice that there are no protons here or here, so there's only one direction for the elimination to proceed. So we could lose a proton, and the bromine form our pi bond and get this product here. So is this the only product that we could generate? Well, in fact, there's one more, and that product looks like this. All right, these two molecules are stereoisomers. And we call this one trans, because the two big groups are on the opposite sides of the double bond, and this one cis, because those big groups are on the same side. Now, stereoselectivity plays a role in reactions like this where more than one stereoisomer is possible as a product. The reaction will be then stereoselective if one of those products is formed in excess of the other. And in this case, just like we saw with the Zaitsev rule, when we do the elimination, the most stable product gets formed in excess. And for compounds like this, the trans isomer will be more stable. So this is going to be the major product. The cis is going to be less stable just because these two benzene rings start to get pushed together, creating steric strain. And so this reaction would be stereoselective. Let's write our definition down here. A reaction is stereoselective if it can form more than one stereoisomer as product, but one or some are formed in excess. All right, let's look at the next example. Again, we have a secondary alkyl chloride, but this time we have a strong base. So what would the mechanism, the likely mechanism be? So this would likely proceed through an E2 mechanism. So we have several possible products. We could have a product that looks like this, right? Because we have H's on this. This is a beta position, and we have a beta position over here as well. This would be trans. So cis is possible as well. cis. And a third possibility here is that the elimination would not follow Zaitsev's rule, and we could get this double bond on the end. All right? So we have possibilities here. We're going to yield the most stable product in excess, and so that is going to be the trans, more highly substituted product. And so this reaction, in fact, is regioselective because we see the double bond located in that internal position and not this end position, and the reaction is also stereoselective because we see trans more than we see cis. In these two examples, we've added some stereochemistry. Let's see if it makes a difference. In the first elimination, we have secondary alkyl halide. We have a strong base, so we have an E2 elimination. The reaction should follow Zaitsev rules, so that tells us that the elimination should go to the beta position that's more highly substituted. So it's this hydrogen here that should be lost in the reaction. So the reaction proceeds, and we get just what we would expect, the most stable product. The second example here is different only in the stereochemistry of the leaving group. All right, it's still secondary. It should still be E2, but by changing the stereochemistry of the leaving group, we change the major product. We get a different stereoisomer. Okay, both stereoisomers are possible for each reaction, but we see a different major product for the top one versus the bottom one. So why would this be? In order for an E2 elimination to take place, the orbitals forming the bonds must be able to align or to overlap. The only way that this is possible is when the hydrogen-carbon-carbon leaving group bonds are coplanar, which means that they're all in the same plane. There's two possibilities for how this can be accomplished. One is for the carbon-hydrogen bond and the carbon-bromine bond, in this case, to be anti to one another, and this arrangement is called anti-periplanar. Anti, we know, is a conformation where two groups are 180 degrees apart. Periplanar means in the same plane. The other possibility is that the carbon-hydrogen bond is in the same plane and on the same side as the carbon-bromine bond. And so this is called syn-periplanar. All right, so these are two possibilities. One of these arrangements is more stable than the other. So which one would that be? Well, notice that the syn-periplanar arrangement is eclipsed, and the antiperiplanar arrangement is staggered. Okay, this in its own right is not enough to make one happen over the other, because sometimes an unstable conformation can still lead to the major product. But in this case, what happens is as we go through the transition state, we'll be generating a delta minus on the bromine, and we will be releasing or relieving the minus charge on the base, so we'll have a delta minus on the base. When we have this as anti-periplanar, these two groups are as far apart as possible. Okay, so the delta minus on the base and on the departing leaving group are far apart in anti-periplanar arrangement. Okay, and so this is the favored arrangement. So let's see how this plays a role in the example that we looked at. So we know that it's this hydrogen over here that we lost. But we know that we have a hydrogen over here as well. So the best way to analyze this situation is by looking at a Newman projection from where I've drawn the arrow. Okay, so let's dredge up how to do this. So remember, the dot is the carbon in front. This carbon has the ethyl group pointing up. The H, if I'm looking at it that direction, is going to be going out to the left. And the methyl group here is going to be going to the right. I didn't center those very good. All right, on the back carbon, remember we put the back carbon with a circle. We have this methyl group going down. We have the H going to the right, and the bromine going to the left. All right, does this have an anti-periplanar arrangement between this hydrogen and the bromine? Well, no, look at here they are, and they're only 60 degrees apart. So for the E2 elimination to take place, this molecule needs to adopt a different conformation. And what it needs to be able to do is move this bromine over here, which is going to force this H to go here and this methyl group to go there. So I'm going to redraw this. I'm going to rotate around. The front carbon is just the same. But the back carbon has rotated the bromine over here, so now it's anti-periplanar to that H. The H rotated down here, and the methyl group rotated over here. All right, so now this bromine and this H are anti-periplanar. Okay, so when the elimination takes place, we need to look at which groups are on the same side. So notice here in the product we have the ethyl group here and the methyl group here are on the same side. So when we draw this product, the double bond here, there's the ethyl group on the top, and so the methyl group at this position has to be on the same side. Okay, here's the same two. All right, and so this is the product that we get from this starting material. All right, this one is in fact not the most stable product because we have the methyl group here and the ethyl group together, and those two groups are the bigger two groups, and so they cause more steric strain. But that is the product we get because of this requirement for the E2 to proceed through an anti-periplanar orientation. What happens when we do E2 reactions in rings. So let's look at these examples. So the first example, we have a secondary alkyl halide, we have a strong base. We would know that favors an E2 elimination. We have the alpha position here, we have the beta position there, and another beta position over here. So we have two possible products. We have the product that goes towards the methyl group. This would be predicted by Zaitsev's rule. But we have another possibility where the elimination could go to the other beta position. In that case, this methyl group would retain its stereochemistry and the double bond would go here. All right, the bottom reaction is only different because the stereochemistry of this methyl group is different, right? So these are stereoisomers as well. So it could yield the same products here. So this one is the same as above. The second one turns out, the way I've drawn them, to be the enantiomer to the one above. Okay, but essentially the concept is the same. If we look at which of these products is the main reaction, main product, in the top one follows just like we would predict. This would be the major product, follows Zaitsev's rule. The lower reaction, however, gives this second product as its major product. So why would this be? All right, so just like before, these eliminations, E2 needs an anti-periplanar arrangement between the beta hydrogen and the leaving group. So how can we tell if there's an anti-periplanar arrangement when we have these two molecules in cyclohexane rings? How does this work in a ring? What we have to do is to draw the cyclohexane ring in a way that we can analyze the angle between the bromine and the hydrogen. And the easiest way for us to do this is to draw the cyclohexane in a chair conformation. So we have to remember how to do this. So I'm just going to pick one of my chair conformations. I'm going to draw it just like we did before. I'm going to add in all of the bonds. And then I'm going to place the bromine and the methyl group. I'm going to start with the bromine is pointing up, and I'm going to put it right here. Just because I like, when I do it, to have one of those groups on the end. It makes it easier for me. You can start anywhere you want, though. So next to it, going in a counterclockwise way, is the methyl group, and it's going down. So I'm going to put it over here, and it's going down, so it's in an equatorial position right now. Let's fill in the rest of the hydrogens. And we get one of the chair conformations of that cyclohexane up there. So here's our leaving group. Can there be a hydrogen and anti-periplanar to it? So here's the alpha position, here's a beta position, and here's a beta position. So when the bromine is in an equatorial position, the bonds that are anti-periplanar to it happen to be these bonds that are in the ring. Okay, and so they are not carbon-hydrogen bonds. All right, so there is no anti-periplanar planar beta hydrogen in this structure. So how do we find that arrangement? Well, what we have to do is we have to do a ring flip. And we have to get the bromine into an axial position. That's the only way that it can have an anti-periplanar hydrogen. So we're just going to redraw this in its alternate chair conformation. I'm going to draw in all the bonds here. There's all the axial and the equatorial bonds. You guys should be pros at doing this by now. And remember that alpha position, if it's the furthest right in this structure, is going to be the furthest right in this structure. The bromine was pointing up in the left structure, so it remains up in the structure on the right. The hydrogen, or the methyl group I mean, was pointing down, and so it remains down. And so it's going to go over here. Draw it here to fit it in. So there's the methyl group. Now let's fit in the rest of our hydrogens. All right, so here's our bromine, and let's look at what groups are anti-periplanar to it. All right, on the side of the methyl group, the actual methyl group here is anti-periplanar, all right, not the hydrogen. And so it cannot eliminate to this side. However, if we go around the other way, we see that this hydrogen is anti to the leaving group. So these two are anti-periplanar. All right, and so the elimination can take place only in that direction and gives us, as the major product, the double bond going over here. All right, so we have to be able to consider this arrangement. So what we're looking for really in our cyclohexane is that we need to have a hydrogen that is trans to the leaving group. All right, so here is our hydrogen here. Those are cis, so no elimination can go in that direction. Over here, because there's actually two hydrogens here, this bromine and this hydrogen are trans, so they can adopt an anti-periplanar arrangement. Notice in this discussion, we are having to adopt a specific stereochemistry to allow the elimination to take place. But this reaction really is not stereoselective. This reaction is regioselective, right? Because the position of the double bond is what changes.